Okay, so Jeff asked me to give you a gentle introduction to the microscopic models. So I don't know exactly what gentle introduction means, but anyway, talking about microscopic models is not an easy task because there are many things to do, many things to talk about. So I'm going to try to give you a general overview and give you the main difficulties, the main properties, and give you some example at the end of my talk. So this is the menu for today. So before entering the problem of microscopic models, I have to speak a little about some important concepts for microscopic models. And one is the isospin, and the other one is antisymmetrization. So maybe this is something you are familiar with, but I'm sure not all of you are. And of course, when you are using a microscopic model, crucial issue is the problem of the nucleon-nucleon interaction. So I will talk about the nucleon-nucleon interaction. And then probably you have heard about the shell model. You know all properties of the shell model. But I will show you that all microscopic models are, in some sense, related to the shell model, can be seen as extensions of the shell model. So I will remind here the basic properties and give the notation for what I need after. And then, well, here I will try to give a short overview of the different microscopic models, because of course there is not one single microscopic model, there are different approaches. And here I will try to give you a short description of these different approaches. And then I will focus more in the generator coordinate method, which in fact is a cluster model. In a cluster model, you assume that your nucleons are grouped in clusters, and this provides some simplifications for to solve the Schrödinger equation. And I will show you here that this generator coordinate method, or cluster model, is not limited to spectroscopy. It can also deal with reactions. So this is a nice property of these cluster models, and a difficulty for other microscopic models. I will mention that later. And then something here which may look strange in this list, which are forbidden states, but this is an important output from the microscopic models. I will show you that when you want to simplify a microscopic model to a non-microscopic model, using optical potential, for example, you can learn something from a microscopic theory, which has influence on the choice of the potential, and this comes from the forbidden states. And then I will show you some example in spectroscopy and in reactions. So the first thing I have to discuss is the definition of a microscopic model. And well, in a microscopic model, there are two characteristics. One is about the wave function, the other one is about the Hamiltonian. So the wave function must depend on all nucleon coordinates. So this is shown here. The wave function depends on the A nucleons and should be fully antisymmetric. We know that nucleons are fermions. So if you exchange the coordinates of two of these fermions, of these two nucleons, then you should get the same wave function, but with a sign minus here. So this is the result of the Pauli principle. And well, the Hamiltonian in a microscopic model is given by this expression, which includes the kinetic energy of each nucleon. It includes a two-body nucleon-nucleon interaction, and in some cases may include higher order terms, like a three-body interaction. But here I put it in gray because in general this term is neglected, and in all my applications this term is indeed neglected. And the two-body nucleon-nucleon interaction contains a nuclear part, which is short range, and a Coulomb part, which is the standard Coulomb interaction, which is a long range term. And well, there are different models because there are essentially two problems. The first is that you don't know exactly what the nuclear interaction is. And the second, even if you know exactly the nucleon interaction, you cannot exactly solve a problem like this with many particles. So this is the whole of the models, to make some simplifying assumptions to end up with a solution of this Schrödinger equation. Okay, so why do we do microscopic models? Well, one of the reasons is that there is, in principle, some predictive power, because there is no parameter, or almost no parameter. Everything is obtained from a nucleon-nucleon interaction. So you have more predictive power than with an optical potential, for example, which you don't know. And some microscopic models also provide you with a consistent description of spectroscopy and of scattering. And of course, this is a nice thing, because we know that both processes are strongly related to each other. So for spectroscopy, you can look at energies, of course, but some spectroscopic properties like radii, electromagnetic transitions. And in scattering, of course, the simplest is elastic, but you have access to transfer radiative capture. And this is one of the reasons why these models are widely used in nuclear astrophysics, because you have access to transfer and radiative capture reactions. And of course, the problems are listed here. So that's one of the differences with atomic physics. In atomic physics, you also have many body problems with many electrons, but there you know the interaction, it's a Coulomb. Here we have a many body problem, but we don't know exactly the nucleon-nucleon interaction. We know some properties, but we have to do approximations about this nuclear interaction. So we use in general effective nucleon-nucleon interactions, which are adapted to the model. And I will tell more about the difference between these effective interactions and realistic interactions. It doesn't mean that effective are not realistic, but this is the terminology. Realistic interaction means that it's fitted on nucleon-nucleon properties, simply. And effective interaction means that it includes the effect of the model. Okay, and of course, the main problem is that you cannot solve a Schrödinger equation with nucleons. There are methods to solve exactly for 3-4 nucleons. And then there are techniques now to go to slightly higher nucleon numbers, up to 12, carbon 12. But this is a real numerical challenge. And another problem is that in most cases, it's difficult to apply to scattering states. And this is why there are various models which all start from a microscopic Hamiltonian, but they differ in the approximations. Of course, the shell model, that's probably you know, and recent extensions with the no-core shell model. This is simply an extension of the shell model without any assumption about a core. So these are huge bases which are essentially applied to spectroscopy. Then there are what are called fermionic molecular dynamics, or antisymmetrized molecular dynamics. I will show you briefly how it works. These are two more or less equivalent. And then cluster models. So here you assume that the A nucleons are grouped in different clusters. And this is called the resonating group method, which has been developed in the 60s. And which is equivalent to the generator coordinate method. I will discuss more about these two methods, which are physically completely equivalent, but I will show you that the generator coordinate method is better adapted to numerical calculations. Okay, so as I said before, before talking about microscopic models, we need two important concepts, which are the antisymmetrization and isospin formalism. And we also need to talk about the nucleon-nucleon interaction. So let me start with isospin. So maybe some of you know, but this is an important thing for microscopic models. So the problem is that we know that neutrons and protons have a different charge, but have very similar properties, almost the same mass. The mass difference is of the order of 0.1%, and we know that there is a charge symmetry. So if you exchange neutrons and protons, you have the same nuclear interaction. Of course, this is not true from the Coulomb interaction, but we know that the Coulomb interaction is weaker than the strong interaction. So we essentially pay attention to this nuclear part. So the idea of the isospin is to consider a single particle, which is the nucleon, with an isospin 1/2, and which can be in two states, +1/2 or -1/2, according to whether it's a neutron or a proton. So for neutron is +1/2, the projection, and for proton is -1/2. And this allows you to write the Coulomb interaction, the nuclear interaction, without specifying whether you consider a neutron or a proton. It's a unified treatment of neutrons and protons. So these are for nucleons. And then for the nucleus, you simply add the projection of all isospin projections. So for the nucleus, the sum here is the number of neutrons minus the number of protons divided by 2. And the isospin number is larger than this projection. So if you consider the nucleon-nucleon system, which of course is very important for the nucleon-nucleon interaction, so you couple two isospin 1/2, which means that you have T equals 0 with a single projection. And this is the well-known deuteron. The deuteron has isospin 0. And the other possibility is to have isospin plus 1. And then you have three projections, -1, 0, or 1. And this corresponds to diproton, dineutron, or excited cell of deuteron. And all of them are unbound, but they belong to the same isospin triplet. Okay, so this is an example for mirror nuclei, carbon-13 and nitrogen-13. Carbon-13 has 6 protons, 7 neutrons, and vice versa for nitrogen-13. So the total isospin are +1/2 for carbon-13, -1/2. And you can see that the spectra are rather similar. And there are differences because of the Coulomb interaction. Of course, the Coulomb interaction doesn't respect charge symmetry, and this is why you have slight differences between the two mirror spectra. And this is another case with 14 nucleons. So you have here carbon-14, nitrogen-14, oxygen-14. And here you may have isospin projection 0. So here you have nitrogen-14. And here you have projection plus 1 here. No, it should be here minus, here it should be -1. So you can classify, in nitrogen-14, you can classify the states. Some have isospin 0, so T equals 0, and are specific to nitrogen-14. And others have isospin 1, for example this one, and then you can find them in the other mirror nuclei. So isospin is a very important concept in nuclear physics. So now let me come to antisymmetrization. So the idea of isospin is to include this isospin function in the nucleon wave function. So each nucleon has an individual wave function which depends on the space coordinate. And well, one example is a Gaussian in the shell model. You have a part which depends on spin, and we know that the spin of a nucleon is 1/2, but it may be in two states, plus 1/2 or minus 1/2. And then with the isospin formalism, we can just add here one additional part to the wave function, which is the isospin component. And again, the isospin is 1/2, and there are two projections according to whether you have a neutron or a proton. So the total, this is for a single nucleon. And then you build the total wave function of the system by taking the product of all orbitals. So here I just wrote the space part because it's shorter, but the spin and isospin coordinates are implied. So each individual wave function depends on the space coordinates, spin and isospin coordinates. And then you have to include the Pauli principle. You know, this wave function should be antisymmetric when you exchange two nucleons. So you must have this property. So if you exchange nucleon I and nucleon J, you must have a minus sign here. And this is not true, of course, if you just take the product here. So what you have to do is to antisymmetrize this product. And then you get antisymmetric wave functions. And this is the role of this antisymmetrization operator A here. And this antisymmetrization operator defines all possible permutations among A elements. So it's defined here. You have an index P going from 1 to factorial A. And factorial A is simply the number of permutations that you can build from A elements. So you can see this number increase very fast when the nucleon number increases. And so you have this PP, which corresponds to a permutation inside the elements. And you have epsilon P here, which is +1 or -1 if you have an even permutation or an odd permutation. And okay, so you can easily consider some specific examples. So with two particles, it's very easy. It contains two terms. One means that you change nothing. And the second term is P12, so you exchange particles 1 and 2. These are the two terms that you expect from factorial 2. There are no other possibility. Now, if you consider three particles, then you have 6 terms. Of course, one corresponds to no permutation, no change in the ordering of the nucleons. And then you have the 5 possibilities here, which represent the number of permutations that you can construct from 3 elements. And some of them have a positive sign, and some of them have a negative sign. So for example, here you keep particle 3 in this position and you change 1 and 2. So it's only one permutation, so the parity, the sign is -1. Okay, and this is true for the rest. And okay, so you immediately see that when the number of nucleons increases, this number increases very fast. So if you consider 4 particles, you have 24 terms, which is factorial of 4. And well, an important property of this antisymmetrization operator is that it's called a projector. The projector means that if you apply it twice, it's equivalent to applying a single time. So A square up to a normalization factor here is equal to A. And you can easily see it for 2 particles. So if you apply the antisymmetrization operator twice, you have this product of the antisymmetrization operator here. If you expand it 1 with 1, it's of course 1. You have 2 times P12 and P12 to the square. And P12 to the square is just 1. You exchange 2 times, so it corresponds to 1. So at the end, you have 2 minus 2 P12, and then you recover what you expect from here. You have 2 times the antisymmetrization operator. So now how to write an antisymmetric wave function? Well, the easiest way is to introduce a Slater determinant. I've shown in the slide before that the wave function is constructed from orbitals, individual orbitals, with the antisymmetrization operator in front of it. And this is completely equivalent to a Slater determinant with the different functions, so phi 1, phi 2, phi a here as the columns, and with in the lines you simply change the coordinates of the particles. So this function is exactly antisymmetric, because if you change 2 columns or 2 lines, you get a sign minus. And if you have 2 nucleons which are in the main state, which means that 2 of these functions here, well, they are A functions, and if 2 of them are identical, then you have 2 identical columns, and then you know that a Slater determinant is 0. And this is expected from the Pauli principle. You cannot have 2 nucleons in the same state, and this is consistent with that. And so this is the Slater determinant, and a shortcut to write this Slater determinant is here, determinants of phi 1, phi a, and this means that you consider this Slater determinant here. So let me again consider a simple case, which is 2 particles. So you start from an antisymmetric product of these 2 orbitals. And of course, this is equivalent to these 2 terms here, and you recover the simple Slater determinant here. And now, if I want to be a little more specific, I consider the alpha particle. The alpha particle has 4 nucleons. So you have a Slater determinant which is 4 by 4. And all nucleons have the same radial part, at least in the shell model, which is a Gaussian 0s functions, like a Gaussian function here. And you know that there are 2 possibilities for the isospin, so neutron or proton, and 2 possibilities for the spin. So this makes you your 4 by 4 Slater determinants. And here, if you include the spin and isospin, the alpha particle Slater determinant is written as here. So you have 4 functions, and the special part is common to the 4 functions. And then you have either the isospin, neutron or proton, or the spin which is defined. So this is the Slater determinant corresponding to the alpha particle. Okay, so we have basis functions, and as usual in microscopic physics or in theoretical physics, we need to be able to compute matrix element between these functions. So we have Slater determinants, and we would like to compute different matrix elements. So the overlap, for example, the overlap between 2 Slater determinants, or 1 body or 2 body matrix element. So 1 body matrix element is a typical 1 body matrix element is written here. This is a 1 body operator, which is a single sum over the nucleons of individual operator. And an example is the kinetic energy. So if you want to compute the kinetic energy of your system, you must be able to compute this matrix element where psi and phi are Slater determinants. So I wrote them here. The root mean square radius, for example, is another example of 1 body operator, or electromagnetic operators. These are other examples. And then when you consider the nucleon-nucleon interaction, these are called a 2-body operator. And you must be able to compute this matrix element with O2. So O2 is a double sum, I and J, because these 2-body matrix elements depend on 2 nucleon coordinates. So let's go for the overlap. So we write here the overlap between these two Slater determinants. So you have on the right side antisymmetrization operator acting of the orbitals phi, and on the left side on the orbital psi. And then we saw a few minutes ago that A square is equal to A with this factorial A here. So we can replace the A square which appears here by A and just including here. And if you now develop this antisymmetrization operator on all different permutations, you immediately find that this overlap is nothing but a Slater determinant which includes the single particle overlap. So you have here different orbitals for psi, different orbitals for phi, and you simply compute the single particle overlaps. And then with the Slater determinants of that, you find what you are looking for, which is the overlap between your two Slater determinants. And there is an additional factor here, which is factorial A, but you can easily get rid of this factor simply by renormalizing the wave function. You just include this factor, and then the overlap between your two wave functions is just a Slater determinant. So the overlap is very simple. So now let's look at the one-body matrix element. So as I said, two examples are the kinetic energy or the RMS radius. They include single sums over the different nucleons. And here I'm sorry for this old style slide, but it's faster for big equations. So I don't want to enter into details, but just show you the main result. Again, you have this operator here. So you do exactly the same as before. You express your Slater determinants as antisymmetric product. And as you see, these operators, they commute with the antisymmetrization, because these are sum over I. So in this operator, you can exchange two particles. When you have the sum of two or three terms like this, you can choose the order as you like. So it means that these two operators here, they commute. So you can change the order here and put O on the left and A on the right. And then again, you have A square. A square is equal to A up to a factor here. And so this is a little bit more complicated than the overlap, but it's rather easy to show that this matrix element is a double sum of individual matrix element times what is called the minor of the overlap matrix. So the overlap matrix is just the matrix I've shown before. It's a matrix with the different overlaps. And Mij here is just a Slater determinant that you get by removing the line I and column J. So again, you just need this single particle matrix element and the minor of this matrix. So this is a very systematic calculation, and involves a double sum here. You have a double sum. Now, the things are a little bit more complicated for a two-body operator, because here you have a double sum. So you repeat exactly the same algebra as before, and then you can express this matrix element as a quadruple sum, IJKL. So you have here individual matrix element and order 2 minor of the overlap matrix. So here it means that you remove 2 columns and 2 lines of the matrix. And you have here 2 terms. One corresponds to the direct, what is called a direct term. So you have here K and L, orbital K, L, and you have an exchange term. Here you have L and K. So this is a specificity of microscopic theories, you have always a direct term and an exchange term. And here, as you can see, you have a quadruple sum. So if you have, let's say, 10 nucleons, you have quadruple sum going from 1 to 10. So it may include many terms. So in practice, the calculation of these two-body matrix elements is the longest part by far. It takes 90 or 90% of your computer time. But the nice thing is that this is rather systematic. So if you define your Slater determinant, you can easily determine this matrix element. It may take time, but to write a code doing that is something which is not very difficult. Okay, so that's it for the isospin and the antisymmetrization. And now an important ingredient in the microscopic models is the nucleon-nucleon interaction. So I'm going to speak a little about this nucleon-nucleon interaction. So we start from a system of two nucleons. So a system of two nucleons is has a wave function which depends on the space coordinates of these two nucleons, the spin coordinates, and the isospin coordinates. And we know that we don't know this wave function, of course, but we know one of its properties is that it must be antisymmetric. So if we exchange the coordinates of nucleon 1 and nucleon 2, we should recover the same wave function but with a minus sign. Okay, this is something that we know, and we will use this property to determine some properties of the nucleon-nucleon interaction. So this P12 operator exchange all coordinates, so not only the space coordinate, but spin coordinates and isospin. So you can rewrite these wave functions in terms of couplings. So S here, capital S, is the total spin, and the total spin is 0 or 1, because you know you couple two spin 1/2, so the result is 0 or 1. And the same for isospin. Isospin is 0 or 1. So if you couple two particles with spin 1/2 to a S equals 0 state, you have the two Clebsch-Gordan coefficients. So these are the individual wave functions. And you can see that this wave function is antisymmetric. You have a minus sign here. So if you exchange the two parts here, you will get the same wave function but with a minus sign. So S equals 0 state, which is called singlet, and singlet, the name singlet is because there is only one projection. For S equals 0, projection is 0, and a singlet state is antisymmetric. Okay. And now, if you look at S equals 1, you have three possibilities for the projection, and the three wave functions are written here. For S equals 1 and minus 1 is very simple. It's simply the product of two wave functions, two individual wave functions. For 1, 0, there are two contributions. But you can see here that if you exchange the two nucleons, so nucleon 1 and nucleon 2, you get the same wave function. Exactly the same, there is no sign change. So this S equals 1 state, which is called triplet state because there are three possibilities, is symmetric. Okay? So that will be important for the rest of the discussion. So we can write that in this simple notation. Let's consider a spin exchange operator, and at the moment I don't specify what is this operator, but let's assume we have an operator P sigma, and sigma is 2 times the spin, so it's a tradition to call that sigma instead of S because it's 2 times the spin. So P sigma exchange the two particles in some states, and for S equals 0, we know that it will change the sign. For S equals 1, we know that it will not change the sign. So these spin exchange operators has eigenvalues which are -1 to the power s plus 1. You can easily see that from here. And now let's specify what is this operator. Well, you can easily show that this operator is determined from the spin operator sigma 1 and sigma 2. And well, to see that, I write here a matrix element of p sigma between two wave functions. So sigma is 2 times the spin. You know, these are called the Pauli matrices, and it's just 2 times s. So sigma 1, sigma 2 is 4 s1, s2. And then you express S1, the scalar product S1, S2 from the total spin. So this is a standard trick in theoretical physics. So the scalar product S1, S2 can be expressed from S square, S1 square, S2 square. And then the eigenvalues of S square are S times S minus 1. S1 square and S2 square provides 3, 4. So these are the eigenvalues are 1/2 times 3/2, so it's 3, 4. So you immediately see that this operator provides you with s plus 1 minus 1. So for s equals 0, you get -1, which is what you expect here. And for s equal 1, you have 2 minus 1, which is 1. So this spin exchange operator, P sigma, is just written like this. So you have the definition of P sigma, and this will be important for the nucleon-nucleon interaction I will talk about in a moment. And of course, you can make the same discussion for the isospin, and you will have an isospin exchange operator, which is written simply by changing sigma in tau. So tau is 2 times the isospin operator. And then if you combine everything, you end up with this operator P12, which exchanges the 2 nucleons. So there is a space exchange, spin exchange, and isospin exchange. So this operator, P12, is written as a product of 3 operators, PR, which exchanges the space coordinates, P sigma, which is written here, and P2, which is written there. So, so what's the consequence of that? The consequence is what is called the generalized Pauli principle. And as we know that the wave function must be antisymmetric, so it means that the product of these 2 operators should be equal to -1. Okay? Because the wave function, the total wave function must be antisymmetric. So the action of this operator, the full operator, should be -1. And now if you look at the phases, the space exchange introduce a phase is -1 to the power L, where L is the orbital momentum between the 2 nucleons. P sigma introduce a phase -s plus 1, and P2 -t plus 1. So if you combine these 3 phases, you end up with a selection rule, important selection rule, concerning the quantum number of your system, is that the sum L plus S plus T must be odd. So -1 to the power L plus S plus T must be equal to -1. So this is a consequence of the Pauli principle, and this is called the generalized Pauli principle. And then, so if you consider a parity plus, so positive parity, so it means that S plus T must be odd. So you have 2 possibilities, S equals 0, T equals 1, or S equals 1, T equals 0. So T equals 0, S equals 1 is here, and it corresponds to the deuteron. So T equals 0 means that you have 2 nucleons with opposite isospin. So 1 neutron, 1 proton. Okay? Because you must have opposite isospin. And this state is the deuteron. And now if you consider the other possibility, T equals 1, So you have three values for the projection. So this is Tz equal +1, this is a neutron-neutron, Tz equal -1 proton-proton, and here you have an excited state of the deuteron. So if you neglect the Coulomb interaction, these three states are at the same energy, and we know that this T equal 1, S equals 0 is unbound. And we know the binding energy of the deuteron is 2.2 MeV. So these properties should be reproduced by the nucleon-nucleon interaction, and I will come back to that in a moment. So this is for even values of L, and of course if you have odd values of L, then you have two other possibilities, 0, 0 and 1, 1. So this must be also included in the nucleon-nucleon interaction, but all these states are unbound. So we know that the nucleon-nucleon system has only one bound state, which is the deuteron, and which is here. So what's the consequence of that for the nucleon-nucleon interaction? Well, we know that the nucleon-nucleon interaction contains two terms, one which is the nuclear part and another one which is the Coulomb part. And the Coulomb part is written here in the isospin formalism. So this is written for neutrons as well as for protons. So you can see here that if one of the two particles is a neutron, so the isospin is +1/2, so one of these two terms is 0, so the Coulomb force is 0. The only way to have Coulomb force different from 0 is to have -1/2 here, -1/2 there, which means that you have two protons, as you expect. And so the Coulomb part is well known, and the nuclear interaction is not known exactly. And what we are going to do is to use the previous results, Pauli principle, to derive some general properties, general form of the nuclear part. So we know that the general form of the nuclear interaction contains different terms. One is called the central, and in fact it's a dominant term. And it's called central because it doesn't change the angular momentum or the spin. We know that there are two possibilities for the spin, S equals 0 and S equals 1. And the central part doesn't change this spin. There is a spin orbit term which may change by 1, and there is a tensor part, and well, I will essentially describe the central term. So then how to use the Pauli principle to determine the general form of Vn? Well, we know that we have a wave function, a nucleon-nucleon wave function. We don't know exactly what it is, but we know that it satisfies two eigenvalues problems. So it's antisymmetric. So this wave function, if you apply the exchange operator, provides you with a minus sign here. So this wave function is eigenvalue of P12. And also we know that this wave function, whatever it is eigenfunction of the Hamiltonian. Okay? And the Hamiltonian contains two kinetic energy terms and the central part of the nucleon-nucleon interaction. And we know that in theoretical physics, that if you have two operators with the same eigenvalues, then they commute, and vice versa. This is an important theorem in quantum mechanics. So if we use that here, we know that these two operators, P12 and H, they have the same wave function, the same eigenstate. So they should commute. And then if you look at H contains this kinetic energy, and obviously it commutes with P12, because T1 plus T2 is equal to T2 plus P1. So what you deduce from this is that the central part of the nucleon-nucleon interaction should commute with this operator P12. Okay? So this is a general property. And now if you go back to the definition of this P12, P12 is the product of three operators. And if you want to write the most general form for this central part of interaction, including this constraint, then you easily see that this central part can be expressed with four contributions, one which does not depend on the exchange operator, one which depends on PR, one on P sigma, one on P2. So this is the most general form which is consistent with this requirement. So all these terms here commute with P12. Okay? And R here is the distance between the two nucleons. So you can exchange the two nucleons, and the distance, of course, is the same. And these terms have specific names. So the terms here, which is independent of any exchange operator, is called the Wigner term. Here you have the Majorana term, here the Bartlett term, and here the Heisenberg term. So I don't know exactly the origin of these names. Probably they meet at some place and share the names for these terms. Anyway, one is independent of the exchange operator, and the three others depend on PR, P sigma, P2. And then you are left with these functions, W, M, B, and H. And these functions are now adjusted to experiment. And then there are different types of interactions. For example, Gaussian forms or Woods-Saxon or Yukawa expressions. But these functions here are fitted to experiment, to reproduce the binding energy of the deuteron, for example, quadrupole moment, magnetic moment, or something like this. So the general expression is written here. So if you consider the system, for example, neutron plus proton, so T equal Tz equal 0. So you have two possibilities, one for the singlet state and one for the triplet state. And if you apply this exchange operator to this state, then you find different signs here. So you can see that you have here two different functions according to whether you have singlet or triplet. And you have here a figure with the Minnesota potential, which is a combination of Gaussians. So these are the neutron-proton nuclear potential for S equals 0 and S equal 1. So you have here S equal 0. This is S equal 1, T equal 0, which is deeper because there is one bound state, which is the deuteron. Okay? And the other component is the singlet component, S equal 0, T equal 1. And here there is no bound states, and this is more repulsive. So you see the range of this nucleon-nucleon interaction is about 3 Fermis. It's almost vanished after 3 Fermi. Yes?
The general expression, when you compare the PR, P sigma
term? Okay, that's a good question. You know that can you see here if I hide here? Loom 1. Okay, so you know that the product PR, P sigma, P tau equal -1. Okay, so if you consider a product of two, PR, P sigma, for example, this is simply minus P tau. So this is why we don't consider the product of two terms, two exchange operators, because they are equivalent to one of them. And in general, one doesn't use PR. So we express PR as a function of minus P sigma, P tau. Okay? Okay. So now a few words about higher order term, non-central terms. Well, there can be many additional terms. I just wrote here a spin orbit term and a tensor term. So the spin orbit term includes the product of angular momentum, the scalar product L times S. So here you see you may have a change in the spin. The tensor force is a little bit more complicated. The operator is written here, it's S12. So you have the coupling of the two spin to operator of rank 2, and here rank 2, and the total is coupled to 0. Then you may have couplings between different values of L and S here. And with the tensor force, if you with the tensor force, you can have a mixing in the ground state of the deuteron. So you have essentially a component with L equals 0, so this 0 here, and in the deuteron you have a small component of L equal to 2. It's called the D component, which is about 5%. So the Minnesota interaction, for example, neglects this tensor component. But if you want to have very accurate calculation, then you need to introduce a tensor operator. So this tensor operator is responsible for the mixing of L equals 0 and 2 in the deuteron. And of course, the quadrupole moment, there is a quadrupole moment for the deuteron. And if you limit the calculation to L equals 0, of course, it would be, the quadrupole moment would be 0. So the L equal 2 explains the quadrupole moment of the deuteron. And well, there are still possible additional terms, Ls to the square, L square, and so on. So in general, these type of potentials are labeled by the number of terms that they include. So the central potential is known as V4 type. The 4 refers to the 4 operators that I mentioned before. And you have traditionally potentials with 8 terms. So they include the spin orbit, the tensor, and probably these 2 operators. But if you look at the literature to very recent and highly sophisticated interactions, they include 14 or even 18 terms. It's this nucleon-nucleon interaction. An example is argon AV18. So these potentials contain many terms. And if you want to look at their expression, they take a full page of physref with the number. But these kind of potential allow to reproduce many data, scattering data, quadrupole moment, polarization, and so on. Okay, so these are general properties of the nucleon-nucleon interaction, and there is another way to tackle the problem, and I just mention it. I will not use that, just mention it for the sake of completeness. If you use the field theory, then you can deduce the nucleon-nucleon interaction from the very beginning. And this is called the OPEP interaction. OPEP means one pion exchange potential. And this is written as this expression here, T1, T2. And this is very similar to what I discussed before, because T1, the scalar product T1, T2 is related to P tau. So if you consider the P tau, which I mentioned before, it contains this T1, T2. So this is more or less equivalent. And the potential V pi here contains the tensor operator. Here, this is related to P sigma. And here you have the radial function, which is a Yukawa function. So it's exponential minus r over some distance divided by r. And the typical length here, lambda pi, is the Compton wavelengths associated with the exchange particle. So the idea here is that the interaction is between the two nucleons is due to the exchange of one particle. And this particle is the pion. So the nucleon-nucleon interaction can be explained from pion exchange. And so this is what you get from this OPEP. So you get the at least the long-range part of this nucleon interaction is a Yukawa function. And the typical length associated with the interaction is obtained from the pion mass, so h bar over mc. M here is the pion mass, and you get a value which is about 1.4 Fermi, which is the typical range of the nucleon-nucleon interaction. And here you have, as I already mentioned before, two variants in the nucleon-nucleon interactions. Either you have realistic potentials which are fitted on nucleon-nucleon properties, many data on scattering, analysis powers, and so on. And well, the typical potential, you may have heard about that, the rate potential, Paris, Bonn, Argon, and in general they are expressed as Yukawa function or Woods-Saxon functions which are fitted to the data. Well, in general they are very complicated, and there are problems to apply to many nucleon systems, because in general if you use these interactions, they reproduce very well the deuteron properties, just because they are fitted on the deuteron properties. But then when you try to use them for trinucleon systems, then you don't exactly reproduce the triton binding energy, which is the indication that maybe a three-body force is missing, but these are very complicated problems. So the other alternative is to use effective potentials which are adapted to the model. And in cluster models, we use shell model orbitals. So these the nucleon-nucleon potentials that we use are adapted to that. And they include some nucleon-nucleon properties. You have here two typical examples, which are the Volkoff interactions, which optimize the description of the alpha and of the oxygen-16 nuclei, and the Minnesota potential, which is well adapted to alpha plus alpha scattering, and also reproduce the deuteron binding energy. But these effective potentials don't include a spin orbit or a tensor force. They simulate the effect of the tensor force by an appropriate choice of the central interaction. So for example, the Minnesota potential reproduces the deuteron binding energy without tensor interaction. So this is the effect of the tensor part is simulated by an appropriate choice of the central interaction. So this is why it's called effective. Yes?
So the one-plan exchange potential is a realistic potential?
Well, it's I don't know in which category it should fall. It comes from the field theory. Yes, it should be considered as a realistic potential, but this is not fitted on any data. This comes from field theory. Okay? And it tells you that there is a tensor component, there is these exchange terms T1, T2, S1, S2, and it tells you about the radial dependence of the nucleon-nucleon interaction. So some interactions use this property, and they want to reproduce the long-range part of the OPEP. So this term here. Okay, so now a few words about the shell model, because this is the ingredient to more complicated calculations. And of course, you probably know about the shell model, but I like to maybe to refresh your memory and to specify my notation. So we know that we start from an Hamiltonian which is written here, which is very complicated to solve. And then the idea of the shell model is to rewrite this Hamiltonian by using a kind of mean field potential, so U here. So we replace this complicated two-body term by one-body potential. So we assume that the effect of the nucleons on a specific nucleon can be simulated by only one term, which is the mean field potential. And then there is a residual Hamiltonian here, which we suppose to be small. So if we neglect this residual Hamiltonian, then you end up with a very simple Hamiltonian, which is a particle independent Hamiltonian. So we replace the A-body problem by A one-body problems. So this is the idea of the shell model. So you can first solve the individual Hamiltonian, and then for the nucleus, the total energy will be the sum of the individual energies, and the total wave function will be the product and plus antisymmetrization. And the traditional choice for the mean field potential is the harmonic oscillator potential. So the harmonic oscillator potential is characterized by a frequency which is usually converted in the oscillator parameter B, which is the oscillator length. Okay, so first, if we neglect the spin, we have this the harmonic oscillator Schrödinger equation, and well, we know the eigenvalues which are given here, the eigenfunctions, and for 0s orbitals we have these Gaussians here. So you have here R over B, and this is the wave functions. So this is the S shell orbitals, which is a Gaussian, and you have different excited states, 0, 1. So 0 node L equal 1 node L equals 0, and so on. So this is something which is rather well known. But now if you look at the degeneracy of these orbitals, when you neglect the spin orbit, the degeneracy is given by the total quantum numbers n plus 1, n plus 2 divided by 2. So it means that you can put 2 nucleons in the n equals 0 shell, 6 nucleons in the n equal 1 shell. So this explains the helium-4, oxygen-16. So if you look at the different magic numbers, this simple approximation explains the magic numbers 2, 8, 20, but doesn't explain the magic numbers beyond 20. So this is an indication that a spin orbit force is necessary. So the next step is to introduce in the single particle Hamiltonian a spin orbit term, L times L scalar product with S. Now the good quantum number is J, which is the coupling of L plus S. The individual wave functions are obtained by coupling L and S as usual. So the notation is NR, LJ, so we are talking about 0 S1 half orbitals and so on. So then you compute the matrix element of L dot S, and well, as usual, it is done by taking G square, so it's a very simple calculation. And you find 2 different values, one positive, one negative, according whether J is L plus 1/2 or J is L minus 1/2. So these are standard result in the shell model. And now if you look at the diagram with the orbitals, then you find out that you can reproduce all magic numbers up to large values, and this is the success of this shell model with spin orbit interaction. And this is in agreement with experiment. And now if you look at the spin for a closed shell, the spin is of course 0, and you can reproduce the magic nuclei for here, and also with different numbers of neutrons and protons. And I will need that in cluster models, because I will show you that cluster models are based on shell model wave functions for the clusters. Okay? So now let me come to, so this was for a single nucleon. Now I'm coming to the nucleus. So in this approximation, the Hamiltonian is the sum of the individual Hamiltonian. So the wave function is obtained from the product of the different orbitals with antisymmetrization. We know that the wave function should be antisymmetric. So now it's a nucleus. So you may have different possibilities to construct a Slater determinants with the same number of particles. So for a given shell, you may construct several basis states, and these states don't have a correct angular momentum J and M. And here I take an example. If you have two particles in the P shell, you know that in the P shell there are 6 functions, 6 possibilities. And how many functions can you build with 2 orbitals in 6 possibilities? Well, this number is 6 times 5 divided by 2. So it means that you can construct 15 Slater determinants which correspond to 2 particles in the P shell. Okay? But these Slater determinants don't have a correct angular momentum. So if you want to restore the angular momentum, what you have to do is to compute the matrix element of J square and Jz between these Slater determinants, and then you get the eigenvalues Jj plus 1 and the eigenvalues M. And from the diagonalization of this operator, you can build shell model wave functions with a correct value of Jm and Gnm. And here is an example, a very simple example with the alpha particle. If you just consider the lower states, you have 2 protons in the S shell, 2 neutrons in the S shell here. So you have only one function, and this function is as a spin 0 by definition. But it's a little bit more complicated if you introduce excitation of the alpha particle. So if you allow one proton to be excited to the P shell, so you will have 6 possibilities here to be in the P shell. And in that case, you would have 2 possibilities for the remaining proton here. So it means 12 possibilities for protons. The same for neutrons, as long as you have a single excitation to the P shell. So it means that in these conditions, you can construct 24 Slater determinants with 1 particle in the P shell. Then you can determine negative parity states. And with these 24 different Slater determinants, you first diagonalize J square, Jz, and then you find your wave function with correct angular momentum. And of course, you can continue like this. So here I just consider n equal 1, but you may consider n equal 2, 3, 4, etc. And if you count the number of possibilities, you will see that it increases very fast. So if you want to make an exercise, you count how many states you can build with the alpha particle up to n equal 10 or 15. There are calculations up to 17, I think. And this is the no-core shell model. So this is one of the recent microscopic models, which is based on the shell model, but without any limitation of the shell. And here I take another example, which is carbon 12. So if you consider carbon 12 in the lowest state, so you fill the 6 protons and the 6 neutrons in the 0p3 half shell. So here it's this subshell is filled. So there is a single possibility because you have four orbitals in the p3 half. You have 4 particles, so a single possibility to fill this shell. So and here the wave function is 0 plus. It's easy to show. But now imagine that you consider the p1 half excitations. So here you would have 6 possibilities, not 4, 6 possibilities, and you can you have to put 4 particles in 6 possible orbitals. So it means that you have 15 possibilities for protons, 15 possibilities for neutrons. So it means 225 Slater determinants. But then instead of having only this 0 plus state, you have other states. You have access to 0 plus, 1 plus, 2 plus, 3, and 4. And if you want to describe negative parity states, of course you have to go to consider excitations above the P shell. But this is just an example to show you that when you start increasing the number of shells, then the number of Slater determinants, or the number of combinations strongly increases. Okay, let's me finish with the shell model before the break. So an important thing in the shell model and in microscopic theories is the treatment of the center of mass. So if you imagine that you consider here 3 nucleons, so the absolute coordinates R1, R2, R3. So the CM coordinates is defined by the average value of the sum here. And you can determine relative coordinates which are defined from the absolute coordinates minus the center of mass. So now let me come to a Slater determinants with shell model orbitals. So you have different orbitals here. We saw before these are Gaussians, for example. And if you look at these Slater determinants, and if you translate all coordinates, so it means that you replace all space coordinates by Ri plus S, so you translate your system, then then the wave function changes. And this is what is called the center of mass problem. It means that if your wave function is here or there, they are different. And of course, this is not physical. The wave function must be translation invariant. It should not depend on the center of mass. And a nice property of the shell model is that you can exactly factorize the center of mass function. So this Slater determinant, which is not translation invariant, can be factorized in a term which depends on the center of mass. This is a Gaussian. And you have here a function which only depends on the relative coordinates. So this is the physical part of the wave function, and this is translation invariant. It only depends on the relative coordinates. So this part is the same here and on the other side of the room. So this is called the Bettenhose theorem, and this is important in practice, because this wave function depends on the origin, and this one does not depend. But there is a simple transformation between them. So the consequence of that is that the wave function psi here is a Slater determinant, and we have seen that it's very convenient to have Slater determinants for matrix elements. I've shown you before matrix element between Slater determinants. So this is well adapted to numerical calculation. The problem is that it's not translation invariant. So it's not a physical wave function. And the problem, and now psi tilde is translation invariant, but it's not a Slater determinant. So there is a problem. Either we are physical or we have simple calculations. So in practice, the calculations are performed with the Slater determinants, and there is a simple correction for the CM motion. So this is the standard procedure with shell model wave function and for the treatment of the center of mass. So we use the Slater determinants because they are well adapted to the calculations, and then there is a correction. And if you consider now matrix elements with this function, there is a theorem which is the Gartenhaus and Schwarz theorem, which tells us that the matrix elements of any operator between these Slater determinants or this part of the Slater determinants, these matrix elements are equivalent, provided that in the operators you replace the space coordinates and the orbital momentum by these expressions where you have corrected by center of mass or by the relative momentum of the center of mass. An example is the kinetic energy. So you have to replace in your operator T minus TCM. So the conclusion from that is that you can easily treat rigorously exactly the center of mass with simple tricks. And this is one of the main advantage of the shell model. All center of mass problems can be easily solved. Okay, I think it's a good moment to have a coffee break, and if you have any question.
In case of shell model, probably, for example, in the case of carbon 12, we have just the 4 particle in the picture, and then we have the 1s, probably there are remaining two spaces in the P1 half shell, and then in this case we have 15 possibilities. This stems from other excitation from the particles from the P3 half shell.
Yes,
Is it possible there's an excitation from the S1 half shell?
yes, but then you have, this is inside the same, here it's between two subshells, but it's inside the main shell. It's n equal 1 shell. So these are two subshells corresponding to n equal 1. Of course, if you include excitations here, then you have more energy, and this corresponds to higher excited states. But of course, yes, it could be. It's possible.
So in principle, we have more possibilities than 15
Yes, 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 yes. But this would correspond, you know the energy difference here, it's small. Much smaller than the energy difference between two shells here. So if you excite S shell to the P shell, then this corresponds to high excited states. And different parity, yes. Okay, so let's have